being human factors people, we're very interested in communication. And I'd just like to acknowledge the contribution of my colleague Sarah Zayed, who's the founder of Zayed Engineering in Brazil and has contributed lots of good ideas to this presentation. I'd also like to point out that human error is everywhere. I see that I have an hour to speak to you, which is very gratifying, but I think this is probably a typo. And I think I should say that I don't take the pessimistic view. The pessimistic view about human error is that humans are made by unskilled labour working at night under poor lighting conditions, and therefore some faults are inevitable in the human condition. I take the view that human error is predictable and preventable, and it's actually part of the learning process. The person who never made any mistakes, never made anything, is certainly true. So what am I going to talk about? I'm going to talk about integration. I'm going to talk about combining retrospective and proactive approaches to error prevention. And I'm going to look at the tools provided in the Human Factors Workbench, which is the vehicle for combining together a whole range of tools, how we integrate different types of analysis, and then I'll draw some conclusions from that. So the name of the game is integration. It's very easy for us to focus on one particular aspect of human factors, which, for example, would be prediction, or maybe incident investigation, or maybe human reliability assessment. But how do we actually combine all of those things to produce an integrated approach? And actually, there's a lot of commonality between these different areas, because basically everything is dependent upon a model of human performance. What is it that drives human performance? And that model is germane when we're making predictions. It's germane when we're trying to understand what has happened in an incident. And we also need it if we're going to do human reliability analysis. And there's a lot of benefits in actually integrating these perspectives together. So in the Human Factors Workbench, which is the vehicle for this integration process, there are four main techniques, and some of them you've heard about already. In some ways, that's not too surprising, because this whole process is based upon the Sherpa methodology, and I think my first paper on this topic was in 1986, I shudder to say, in Knoxville, Tennessee, in the American Nuclear Society. So these techniques go back a long way. So there's nothing hugely unique here, but what I think is unique is the way that we can combine them together. So hierarchical task analysis describes how a task is actually done. So we actually get a task description by working closely with operators, comparing the ways that people do tasks across different shifts, and finding out what the truth is. What is the reality at the sharp end? And we can use that for procedures design, for training, and also for risk analysis, as I'll show in a moment. The second technique is predictive human error analysis. One of our earlier speakers referred to this as a human HAZOP, and it's quite similar to that. Again, that was set out in the 1986 paper, so it goes back a long way. Essentially, it's analogous to the process of asking what-if questions. What type of failures can occur, and then what do we do about them? The step analysis, sequential timed event plotting, again goes back a long way, originally developed by somebody called Benner. Another name for it is swim lane diagrams, which is a way in which you represent the sequence of events in an accident sequence. And as you can see, once we've established what happened, then we can start asking why, and that's when we start combining these techniques. And the third technique is called MITRE, Measurement and Investigation Technique to Reduce Errors. And this is basically a variant upon a process of evaluating the performance influencing, or as we call them, or performance shaping factors that drive human error. So all of these things together can be used interchangeably and in an integrated way to manage risk. So let's look at qualitative prediction of potential errors. That's one of the application areas. Stage one, task analysis. It documents what people actually do. It's the starting point for any sort of analysis, because if we don't know what people really do, we can't risk assess it. And it supports procedures development and training. So the structure of a hierarchical task analysis starts off by setting up first of all, the preconditions for the task. What are the assumptions before we start? So in this particular task, which is to take a propane tank out of service, the assumption is that it's part scheduled maintenance has been done, personnel are available, and the system is offline. We then take the overall objective and break that down into sub-objectives governed by a plan. So we have to isolate all the flows to the tank, depressure the tank suction line, and disconnect the tank suction line. Those are all sub-tasks. When all of those tasks have been done, the top goal has been achieved. So we do a validity test, a completeness test. If we've done all of those things, we've taken the propane tank out of service. We then do a risk ranking process based upon the criteria of based upon the criteria of severity of consequences, likelihood of error, and probability of recovery. And we use those three criteria to decide which of these subtasks we break down in more detail. It's this dry text and atmosphere. Coming from a wet country, I'm not used to it. So, using those three criteria, and we do this process every time we break down a task into more detail. We say, what do we really need to break? How further do we need to break this task down? So that risk ranking criteria of severity of consequences, likelihood of error, probability of recovery, suggests that task number 2, subtask number 2, depressurize the tank suction line, has the most risk. So we're going to break that down further into 2 further subtasks. Connect the LPG hose room from water draw valves, fit the pressure gauge to the flare line, and ask operations leader for permission to depressurize the line. Okay? So this is a very structured process, and you can see that it's a great process in which to design procedures because it breaks things down into logical groups. We call it the chunking principle. So here is a typical procedure that might be developed from that process, and you can see essentially we're taking the bottom levels of the analysis. We define what's going to be done, who's doing it, warnings and cautions, and additional information. All of this stuff, by the way, is generated by the software tool automatically. Second stage, predictive human error analysis. And as we said earlier, this is to do with identifying and evaluating the consequences of error. And it uses a set of guide words to prompt the analyst about possible errors. So here is some examples of the guide words. They're divided into 4 categories: action errors, checking errors, information retrieval errors, and communication errors. And we apply these guide words to each of the subtasks or steps in a subtask that we have and say, could this operation be omitted? Could it be done? Could you do the right action on the wrong object? Could you do it in the wrong direction? And so on. And similarly for checking and similarly for information retrieval, which is to do with getting information from screens or procedures, or communication errors. So all of the commonly occurring characteristics that we find in almost all tasks are covered. This is the sort of thing that comes out from a predictive human error analysis. So for a particular task step, prevent the suction line to flare, which we looked at earlier, a potential failure mode is operation too short. In other words, not getting the pressure down to 5 psi as required. The consequence would be that we vent too much propane to atmosphere at the next step. The existing risk control measure is that there is a limit of 5 psi clearly stated in a checklist. However, the fact that there are passing valves in this situation that actually make it almost impossible to achieve that criterion. There's a lot of time pressure to get the job done. The issue isn't addressed in training. There's no local indication of pressure, and operators may move on to other jobs whilst the venting is taking place. So these factors would not be readily apparent unless you actually sat down and did this analysis with people. And out of that, we have actions like, in training, explain the reason for the requirement to achieve 5 psi, ensure the limit of 5 psi is clearly stated in a checklist, supervision, equipment design, install a local pressure gauge, redesign the passing valves. We can do similar things here. Operation incomplete. We could have more than one failure mode for each step. Failure to return water draw valve to normal state after venting. This could lead to an uncontrolled release if returned to service. And there is a risk control measure. There's a requirement to complete a short-term loss defeat form. However, customer practice is that people don't do this. So again, we have to address that by training and also communicate the consequences to people. So that you can see that's a very valuable process to do, and it's a very powerful method of training, as a matter of fact. And we always use groups of people from different shifts, so we get a cross-shift perspective on how this is done. Third stage is how do we evaluate the factors influencing error likelihood. So we've identified some failures, and what do we do about assessing the likelihood of failure and just delineating what we can improve. Well, this is an extract from the software. You probably can't read it very well, but essentially we could put in any human error model that we like. But this is a generic model, and it says that human error is a function of 6 major areas: the task environment, fatigue, procedures, teamwork, expertise, and culture. And in the software, if we click, for example, on distractions, it says there are considerable distractions present when carrying out this task. Do you strongly agree or strongly disagree? And you move the slider up and down, and that generates a score for that particular factor. So this is a way that psychologists use to facilitate consistency in evaluation. But this model, so we have major factor areas, and we actually can calculate a score for the major areas by evaluating the sub-factors under each of those 6 major categories of task environment, fatigue, and so on. And this uses a linear additive model, and all the calculations are explained in detail in the paper. One of the outputs from the software is a profile of the factors influencing error probability. And this is the profile for the 6 major groups of factors that we have. And at the top there you can see a quality index. Quality index is calculated such that if all the factors were at their ideal or optimal value, that quality index would equal 1. And if they were all at their worst case value, it would equal 0. Now, if we can put in calibration data, and it's possible to do that from published sources, we can actually transform that index into a probability. So for this particular task, the quality index is 0.53, and using the calibration equation, and go into the mathematics of what there is in the paper, you can have a logarithmic relationship or a linear relationship. Anyway, the probability there is 0.00, I guess we should call it 0.009, given the comments about decimal places that we heard earlier. So, how do we use those things in combination? Well, we use the HTA and the fear analyses to predict the failures in critical tasks. Of course, before we start this, we've done a criticality analysis, a risk ranking analysis, to decide which task to look at. We don't want this degree of detailed analysis for everything. So we again use the criteria of severity of consequences, probability of failure, and likelihood of recovery to decide to risk rank the tasks that we look at in the first place. We apply MITRE to evaluate the performance influencing or performance shaping factors, and then we evaluate the most cost-effective prevention strategies. And of course the software allows us to do quite sophisticated what-if analyses where we see how the failure probability changes as a result of changing the factors. We can also build in cost functions. We can look at how much money can we save and how much money do we have to spend to get these particular results. What about retrospective incident investigations? We've talked about prediction and prevention. What about how do we have to think about prevention? So we use the STEP process, and again this is another module of the software, and that tells us what failed, and then of course we're going to be interested in why did it fail, what's the most cost-effective intervention, and then this is where we apply MITRE to the process. So let's have a look at a little case study. In this particular incident, there was an exothermic reaction caused by water circulating in a jacket. The circulating pump failed and the reaction went out of control. Unfortunately, a critical pump bearing hadn't been lubricated during maintenance. That would have been fine if the low flow alarm had been working, but unfortunately it hadn't been because it had been overridden at startup and not reinstated. Standby pump would also have solved the problem. Unfortunately, it was out of service. And the reactor exploded. You could say a HAZOP should have been done. So this is what the swim lane or step representation looks like. We start off with the end state, the explosion, the reactor overheats. Then we say, well, what preceded that? The bearing wasn't lubricated. So on the left we have a list of agents, and in the center we have a list of events. So those are the events: bearing not lubricated, bearing fails, pump fails, reactor overheats. What led to that? Well, the maintenance technician didn't maintain the bearing correctly. He also took the spare pump out for maintenance. Spare pump not available, so a layer of protection was removed. And panel operator started up the system, failed to reset the low flow alarm after startup, so another layer of protection was taken away. and there was a failure to detect the pump failure and led to the incident. So the software gives you a very nice tool for doing this, and in fact it transforms the task analysis, the HTA we talked about earlier on, into a step diagram automatically. So what starts off as an analysis of a task, we can say, okay, let's look at that, let's analyse the task, let's turn it into this diagram, and let's see where the failures occurred in that task. So in combination, we developed the incident sequence using STEP. We identified the critical failures in the accident sequence, possibly using fear. Then we apply MITRE to assess the factors contributing to those failures. So the whole process is logically developed, it's integrated, and it saves us quite a lot of effort to do all this. So let's, in conclusion, well, perhaps I should say, does it work? Do we have any evidence? Well, as far as the task analysis of fear is concerned, in the mid-90s we applied this in one of the largest refineries in the UK, in the northwest of England, this was following a flare line incident, and after the first year there was a saving of $500,000, mainly from speed-ups in getting the shutdowns and start-ups carried out more efficiently. And over 4 years, this particular refinery started off by being fairly low down in the international performance levels, but by the end of 4 or 5 years it was in the top, it was at the top, and savings have been more like £4 million. So not only was there substantial improvement in the safety performance, but there was substantial improvement in the efficiency of operations. So we find that the whole process provides a very good environment for applying human factors techniques. The combination of proactive and retrospective analyses is a very efficient strategy for managing human error. Normally these things are not integrated in any systematic way. The software support greatly reduces the amount of effort that you require. And we've seen this whole process applied in a number of organisations across the world. It's currently being applied in UK multinational organisations to satisfy the health and safety executive requirements to verify and validate that human factors has been taken into account in process risk analyses. So we think this is a good tool. If you want a demonstration version, you can go to our website or send me an email. The demonstration version is free, fully functional, but there are limitations on the size. But I would recommend these methodologies for you. None of the methodologies is dependent upon the software, by the way. You can do them by hand if you want to. But the important thing is the integration, and the time has shown that these tools and techniques are efficient and effective in managing human factors risks. Thank you.